So please don't say correlation is not causation again. I'm here to talk to you about correlation, causation, and what machine learning has to say about disentangling these two very important concepts. I'm not supposed to be here on stage. I'm supposed to be in the audience with all of you. Bernardo could not be here last minute, so you're stuck with me for the next 20 minutes or so. When I was, mic check, okay. When I was promoting this presentation on LinkedIn last week, I think some of you will appreciate this story. So it's in bold-face, this title. And I got some comments, kind of interesting. People were curious, what do you mean? What should I say instead? One of the commenters unexpectedly was from our head of compliance, who said, hey, is this for me? Is it because I said that? And I didn't know how to respond, so I just gave him the funny emoji response. I think that we have a lot of model developers in the audience today. Have any of your stakeholders ever said this to you? After you've worked hard to develop a machine learning model, you've shown your metrics, has a great recall, has a great AUC, and then the stakeholder comes and says, well, correlation does not imply causation. Anyone been in that situation before? 2 people? Okay, well, you either don't need to deal with compliance or regulation, or you got lucky. I think all of us at some point in our lives have said these words ourselves. When I'm in that situation, sometimes I'm not sure how to respond, because we know that correlation does not imply causation. That's true. But does that mean that the models we develop are not useful? No. Does it mean maybe we should do a little bit more in this area to disentangle these two? Probably. So I'm a big fan of XKCD, and so is Bernardo, apparently. I used to think correlation implied causation. Then I took a statistics class. Now I don't. Sounds like the class helped. Well, maybe. So where do we go from here? The reason why the title is because that statement is, in my opinion, overused and doesn't really give us a way forward. It's like, okay, that's true, but what do I do now? Another great website is one called Spurious Correlations. I don't know if you know it. They've got 30,000 examples of some pretty convincing time series and data that show, in this case, a divorce rate in the state of Maine in the US with per capita consumption of margarine, which is a butter substitute. They look pretty well correlated to me. One of these caused the other? I don't think so. But in all of these kinds of situations, we have either A causes B causes A, or some other latent factor influences both of them in the same way or in a similar way. So when we're working at a business or some organization, most of our questions are actually causal questions, and most of our tools are statistical tools. But we don't need causality for everything, right? If we look at the weather forecast, I think Bernardo must have clipped this from back in the summer in Lisbon, not from these days here in Porto, but I can predict with very high accuracy what the weather will be tomorrow, but we don't care about causality here because there's nothing I can do in the meanwhile to affect that outcome. And that's what we really want. We create these models to give us information to make a decision, and whether or not we make that decision could lead to some outcome. So in the case of customer churn, there's a talk later on in this session specifically on this topic. I want to know, if I dip my hand into this fishbowl and make a change, is that going to keep my customer or not? About the weather forecast example, I do think, however, there in long-term analysis, I wouldn't be surprised if people are using causal inference techniques for our effect on climate change. So why is correlation not enough? Here you see a box plot for the NM score. What is that? That's a Brazilian national exam, kind of like the SATs in the US. And what this data shows is that if the student has a tablet in their classroom, they get higher scores. And there's a strong correlation, and the effect is true. This is simply fact. But what I want to know is, should I be, as a policymaker or as an administrator in the school, should I be buying tablets for all of my students so that they get better scores on their exams? So this shows the average treatment effect, the treatment being I purchased the tablet for students or not. But I want to know on an individual student level, should I get them a tablet? Now, if I'm a tablet vendor, I might naively or even on purpose stop here and just say, look, buy for all of them. But if I have a limited budget and I'm the one purchasing the tablets, I want to make sure that that act of purchasing the tablet will lead to a positive outcome. Poetry time. Two roads diverged in a yellow wood, and sorry I could not travel both and be one traveler. Long I stood and looked down one as far as I could to where it bent in the undergrowth. So this is a quote from Robert Frost. I think, why is this included here? This random poetry break. The concept of causality is not just related to data. Humans have wondered about causality for a very, very long time. Correlation's fine, but what if? This is a very human thing to want to understand and to know. Now, a little bit away from poetry, if you like some formalization and some math, I have some very light math for you. So that treatment, TI, 1 if the unit received the treatment. A unit here in the example of those test scores is a student. And 0 otherwise, so it's simply a Boolean. And in most areas of causality, we can think quite simply like this. Did the person, did the customer, did the student receive the treatment or not? And then YI is the actual observed outcome, the test score. And that's what I just said. So we can look at this at the individual unit level, which is very important for decision making. Right? We can get an overall average treatment effect, which is important, but what we actually want to know is at the individual level. And that can be calculated quite straightforwardly. If I have that outcome for a particular unit, for a particular person, if they have the treatment, I subtract if they did not have the treatment, and that's the individual treatment effect. That's usually what we're after. And then we also have the average treatment effect. This is also important. This is also useful. Often this is the first thing you would get. And this already tells you something about if I'm affected by this correlation is not causality, ambiguity. But then usually we want to go one step further. So if you were thinking there, is it really the tablet? Is it the tablet that made them have a higher test score or not? Here is if we look at another variable, another feature in your machine learning model, if you will, one that you should probably include, which is, what was the tuition? What was the cost of that school that the student went to? Tablets are not cheap, say roughly €1,000 or so. Not everybody can afford a tablet. If you can afford to go to an expensive school, you can probably afford a tablet. If you cannot afford to go to an expensive school, maybe you cannot afford the tablet. So and those underlying sociodemographic, socioeconomic differences are at the root of a lot of these things. So it's not really the tablet per se, though you can see the data has some scatter here, right? So it's not you can see more blue points on the left and more red on the right. So then we can try to look at this and see, again, on average, we see red dots in the upper right, blue dots in the bottom left. If you go to a more expensive school, you tend to get better scores. Is that because of the tablet or not? On the bottom left graph, you can see, what if I look at that y1 minus y0, the student if they had a tablet or if they did not have a tablet. That difference is what I really want to know. The problem, of course, is that it's hard to go back in time, and or even if I started now, I can't give a specific student both a tablet and not a tablet, and say take the exam twice or something like that. So disentangling this is tricky. So what do? Well, randomized experiments. Very exciting stuff. Very commonplace if you're, for example, in work in pharmaceutical industry, for example, or in medicine. You have a treatment group and a control group. Somebody gets the drug that you're developing, somebody else gets the control. Now, having this kind of setup is often extremely expensive, often not logistically possible, and sometimes, especially with machine learning, I have a lot of historical data. I can't go back in time and do a randomized experiment. What can I do with my previous data to still help answer this question? So what do we do when we can't do a nice randomized clinical experiment here? Well, we can use causal machine learning. I think a few years ago, 5 years ago, this was hardly a topic and has really started to grow in popularity, and people are giving it a lot more attention now. One of the main reasons in my mind for that is because we can use standard techniques that we already know as data scientists, as ML engineers, with very little modification, it turns out, to answer this question about both average treatment effect and individual treatment effect. Whereas previously, it's not like people didn't know what to do about causality, but you needed to make a lot of assumptions. You needed to understand how your variables were interrelated. You needed to make directed acyclical graphs. It was quite a lot involved. And so machine learning offers us a bit of a shortcut based on historical data that we already have to answer these questions. And I think that for me, that's quite appealing. So this I showed before. Good to keep in mind, we have the individual treatment effect, say per customer, and the average treatment effect. I'm going to focus mostly here on the, let's say, the simplest thing you could do, which is the S-learner. And in general, these machine learning, these causal machine learning techniques are referred to as meta-learners. There's the S-learner, the T-learner, the X-learner, the R-learner. There's a bunch of them. And the work on this continues. But I think that the S-learner is already such a simple approach and actually quite powerful, at least as a starting point. And in some ways, it's actually better or more robust than, for example, the T-learner, which I will show on the next slide. So what are we doing here? Basically, we're taking that treatment variable, that Boolean, did they get the treatment or not? Did they get the marketing email that encouraged them not to leave my company? Did an analyst reach out to them when we saw an indicator that something was wrong in the customer account? Did the fact that an analyst reached out to them, did that prevent them from going into a negative balance with me? We include that as a feature in our model. That's basically all you have to do. And that's data we typically do have historically. So you include that as a feature in your model, and then you run your model at inference time. The model's already trained at inference time, and you change that variable to a 0 or a 1, regardless of what it, because we don't know at the time of inference. We're trying to answer that question, should I send them an email or not, to prevent churn. So we calculate that for t equals 1 and t equals 0. We run that through the model, and we literally subtract the two. And that difference, that uplift, tells us about whether or not us taking an action will lead to this or not, will lead to the desired outcome or not. The T-learner is also very interesting. So instead of having that variable t, the treatment, in a single model, you create two models. Now these models can be anything. It can be a linear regression, can be a boosted decision tree. it doesn't matter, which is a huge benefit of all of these methods, is that they're model independent. Use your favorite model, apply these techniques. So here at inference time, you would take the model that has been trained on your control group, your t equals 0, and the outcome of your other model that's trained on the t equals 1, the treatment group, and then you subtract the two. Now, this sounds a bit cleaner, apart from having to maintain two models, but you do need to be careful here because is your model calibrated, for example? If your model is not calibrated, rather if your two models are not calibrated in the same way, you're going to be subtracting very different numbers that are on different scales, and this could lead to you making some bad decisions. So essentially, I feel like causal ML encourages us to have calibrated models or be stuck with simpler approaches like the S-learner. Now, if I want to know average treatment effect, let's take the simplest case. I have a linear regression model. I train it. I include t as a variable. The coefficient of t in my linear regression is literally my average treatment effect. It's just right there. Just get the coefficient, and that's the average treatment effect. Quite powerful. If I'm using a boosted decision tree, we could talk about SHAP and other ways to measure feature importance. I'm going to skip the X-learner here. This diagram has got a lot of arrows in it, and which doesn't make it particularly easy to understand, but it's an extension of the T-learner, except you take the outcome of the T-learner and feed it back into the original model to weigh your samples. Let me give you a concrete example to wrap up here. Marketing campaigns. So which customers will buy my product? If I send them an email. Pretty much every company that I know of has to deal with this question. And we might build a model, churn prediction model, but it's built around correlation. But I want to know more than that. I don't just want to know the probability of the customer buying a product if I send them an email. I want to know, did they buy my product because of the email? Because if they didn't, I could just skip that, right? So that takes us to these four classic segments here. You have the sure things, already happy and satisfied. You have the lost causes. Yeah, they're not going to buy your product regardless. You have the sleeping dogs, very interesting category. They might have bought your product, but actually, because you sent them an email, they're sick of marketing emails, and now they're not going to buy your product. I definitely don't want to send them an email. Then you have the persuadables. Interested on the fence, maybe that email could be the deciding factor. So for the sure things, we should probably save some time and money and not even bother sending them an email. Okay, an email costs almost nothing. But what if we were offering them a discount on our product? That does cost us something. And we have the lost causes. Even if we reach out to them, they're still not going to buy our product. Tier, but let's move on and target the customers that are interested. We have the sleeping dogs. Just let them sleep. Don't send them an email. They're going to naturally buy the product anyways. And then the persuadables. And this is the customer segment that we're interested in knowing the individual treatment effect in order to target these people. So in conclusion, check that historical data. See what you can reconstruct if you don't have that data cleanly. Do we see where we've had a treatment? Some kind of interaction where we've entered into the system and sent an email, or a customer service rep has reached out to a customer, an analyst has reached out to a customer. Take those as our treatment data points, choose your input features, and do causal modeling. Thanks.
Thank you, Ryan. Great talk. We have a couple of questions. Maybe
Sure.
We should just sit for a bit. A couple of questions from the audience. So the first one is, what's your decision strategy to choose a causal model approach for your problem at hand? Do you have one?
I'm a little old school. I usually start with the statistical model because in many cases, we don't need a causal model to have a model that can be effective and bring value to our business. There was a quote earlier in another presentation said something like, machine learning will partially solve almost all problems. So I think there's inherent value still in developing the models that we have. I think many of us have proven that these models do work, but maybe they don't work as well as we thought they did, or maybe we can do even better by bringing in causality.
But what is that then? What is that inflection point where you feel that you need to bring that extra capability, that causal capability into the picture? Is there an inflection point? Like, what is the decision factor?
Maybe you weren't simply aware of that this was an option, that it was an option that had a relatively easy solution. I know most of the data scientists that I speak to, they know this is an issue, but they don't exactly know what to do about it. So I think maybe by hearing a little bit about it here today and also in the next two presentations, maybe this inspires you to do a little bit more in this area.
Great. So one more question. What approaches would you suggest for applying these causal modeling techniques to, in this case, time series data?
Well, the techniques I mentioned are not just for classification. So I was focusing on kind of classification type approaches, but these can be used for regression analysis as well. And in general, I think starting off with the S-learner is simple and can be effective. And then from there, you start to get a lot of additional options, and not just the T-learner and X-learner that I mentioned before.
Great. Yeah, we have time at least for one more. What is your advice for when we want to take the drivers over a certain causal outcome instead of just kind of predicting it, right? We want to understand kind of what were those drivers for the causal relationship.
So in the end, we have a machine learning model, like in that example of the linear regression. It's all tied up with model explainability, in my view. So I think using standard tech, since you have a standard machine learning model kind of at the end, you can also use similar methods like SHAP, for example, Shapley values. And this might help you identify, for example, you want to decide, once you have this individual treatment effect, you want to decide which of your customers to target, to take action, to have a treatment. So you can look into kind of clustering your customers by this uplift in individual treatment effect and decide to target some and not others.
Yeah, that makes sense. And kind of just a final one on derivative of this one. When you actually use these causal models, do you find that stakeholders also understand and really kind of buy into the solution, or do you feel that there is a struggle there? And do you feel that using this approach is easier to convey or harder to convey compared to kind of the regular A/B testing?
Well, I think this approach is nice because sometimes you cannot do A/B testing or you don't want to do A/B testing. For example, in the fraud case, if I can't just say, oh, I have an indicator that somebody's going to commit fraud, but I'm going to decide not to do something just to get good data. So I don't think always A/B testing is possible. And in terms of convincing stakeholders, I would say convincing stakeholders is always challenging. Even when building simpler models like logistic regression models, it can be, even though these techniques have been around for a long time, it still presents a challenge. So I think if you can explain what you're currently doing in terms of modeling, you should be able to explain this as well to your stakeholders and then have a nice extra selling point, which is that, yes, we do know that correlation is different than causation.